This is our learning unit 6 on transition metals. So for this learning unit 6, it will be divided into 4 different parts to make it shorter. And today I will discuss on the part 1 of the learning unit 6, which is the transition metals. So for LU4 and LU5, you have learned on the periodic table of the main group elements. So today we are going to focus more on the transition metals. So if you look at your periodic table here, so in the middle here is what we call as transition metals. So transition metals are d block elements that have electron filling up the d orbitals. So transition metals can be divided into 3 different groups, which is the early transition metal, middle transition metals, and also late transition metals. So if you look at the boxes in yellow here, you can see that if you move across the period, so the electronegativity of the transition metal will increase. Metals are usually having their own properties, but transition metal have their own unique properties. So the first property is transition metal can form colored ions and compounds. So if you look at this picture, you can see that cobalt 2 plus ion can form a pink solution, nickel can give you a green solution, copper 2 plus can give you a blue solution, and sometimes green, and diamagnetic compound like zinc 2 plus can give you a colorless compound. So other than that, transition metal also can form compounds with profound catalytic activity, meaning that for organic reactions, normally a catalyst that is employed in the reaction comes from transition metals group. And then transition metal have another property which is very important, which is they have large charge to radius ratio. Okay, and then the other one, the other property is having high melting and boiling points, and also hard and have high densities, and they can also show variable oxidation state. Okay, let's take a look at the third property, which is the having large charge to radius ratio. Okay, if you look at this graph represents the radii of transition metals as a function of group number. Okay, from this graph, you can see that there are 3 lines here. So the red line represents period 4 transition metals, while the blue lines represent the period 5 transition metals, and the green one here represent the period 6 transition metals. So if you look at the period 5 and 6 here in the graph, you can see that they're actually having virtually the same radii, meaning that the size is not that much difference. Okay, for example, if you look at the group 5b, so this group 5b, it belongs to titanium of period 6 and niobium of period 5. So they're actually having the same size or same radii. So why is this happening? This is due to the lanthanide contraction or lanthanide effect. So this effect actually has its origin in the lanthanide series, which consists of elements 57 through element 70. So the filling of 4f orbitals through the lanthanide elements, it causes a steady increase in the effective nuclear charge, thus producing a size decrease, which is also known as lanthanide contraction. Okay, another reason is that comparing to S and P orbital, F orbital have poor shielding effect. So what does it mean by shielding effect? So let me give you an example. Let's say you have a nucleus here. In the middle, you have a nucleus. So this nucleus is represented by a K-pop star, for example, yeah? Okay, so this K-pop star, it has bodyguard here that protects him from his diehard fan, for example. So this bodyguard is I put it as X. So this bodyguard is actually inner proton. So inner proton. Okay, now you have another one, which is another layer, which is the diehard fan, which I can take it as F, yeah, F. So what happened if you are using s orbital? If there is s orbital inside, the inner orbital is the s orbital. So what happened is that this X will repel the F. So if it repel the F, so F cannot make any interaction with the nucleus, meaning that it cannot reach the nucleus because it is shielded or protected by the X. Okay, let's say if you have F orbital, for example, this is nucleus in the middle, and then you have F orbital as the inner orbital. You know that F orbital looks very complicated. So what happened is that when you have the X, although there is inner proton, but what happened is the X is scattered. This size is very big, and it has scattered X, meaning you have if you have F at the outer orbital, so it might interact with the nucleus through the loophole that is created by the X because it does not have a good shielding effect. So in this case, the F can interact with the nucleus, causing the size to be decreased because F is electron, so in the middle here is nucleus, so nucleus will attract F closer to it, giving you a smaller size atom. Okay. That's all about the radius. Okay, now we move on to the physical properties of the transition elements. So in this case, if we look at the density, it is gradually increasing from scandium to copper. Okay, from scandium to copper, it's actually gradually increasing. So why? Because when you move across the period, the effective nuclear charge increase with the relative to increase in the atomic number. So if atomic number increase, meaning the mass increase, thus it cause the density to be increased. Okay, now let's take a look at the melting point and boiling point for group 1A and 2A elements. Yeah. So if you look at here, why you look at the melting point and boiling point, it is very high compared to alkaline and alkaline of metal. So why is this happening? Is due to the metallic bond in the transition metal. So the metallic bond is very strong because of the delocalization of electrons facilitated by the availability of both D and S electron. Meaning that you have strong metallic bond due to the electron can delocalize between D and S electron. For example, if you see the 3D, normally transition metal has, you fill in the 4s first, and then after that you fill in the 3D. But then sometimes this S can move, electron from 4s can move to 3D due to some reasons. Yeah? So that's why it encourages a strong metallic bond. Okay, next property is when we take a look at the oxidation states. So normal metal, for example, alkaline F metal or which group 1 metal, for example, a potassium. Potassium only have one oxidation state because it is from group 1. But transition metals, they are unique because they can have quite a number of oxidation state. So if you look at the table here, this is for period 4, period 4 transition metal. So if you look at the early transition metal, meaning from scandium, titanium, and vanadium, so the oxidation state keep increasing. For example, if you look at scandium, it only has one oxidation state, which is 3+. But when we move on to the titanium, it has 4 oxidation state. And then when you move to vanadium, it gives you 5 oxidation states. So going down here, so the transition metal are more electropositive, so they are willing to lose valence electron. But if you look at the late transition metal, so this is the late transition metal, okay, the nuclear charge increase. When nuclear charge increase, the metals become more electronegative. Okay, that's why the oxidation state is decreasing. Okay, if you look at the lower oxidation state compound, lower oxidation state meaning like zinc and scandium, they has lower oxidation state. They tend to form ionic compounds when react with another element. But those with higher oxidation state, they tend to form a covalent compound. So from this table, we can also see that the stability of high oxidation state will decrease. For example, manganese 7 and iron 5, they are a very powerful oxidizing agent. Okay, these oxidation states also influence the redox potential value of an element. So meaning to say that if they have higher positive value of E, meaning the element has stronger oxidation ability, which means itself can easily be reduced and serve as cathode in an electrochemical tank, for example. So this E naught value can indicate the possibility whether there will be a spontaneous change from one oxidation state to the other. Okay, let's take a look at the reduction potential ability. If you look at the left side of the transition metal, which the titanium, zirconium, and hafnium, so the metal becomes more electropositive when they go down the group. When they go down the group, they become more electropositive. This means that the reduction ability becomes stronger when they go down the group. So if you look at the value here, meaning when it goes down the group, it becomes more electropositive and they can reduce other element. So if you look at the middle of the transition metal, there is little difference when you go down the group because the reduction potential doesn't have any much difference. But if you look at the right side of the transition metal, okay, which is nickel, palladium, and platinum, so the elements become more electronegative when going down the group, meaning the value of this become more positive because they are more electronegative when they go down the group. Okay, so this slide is the end of learning unit 6 part 1. So I will continue the second part on the next video. Thank you very much.